So that will be Kevin Kennan speaking on a geologic model for lunar ice deposits at mining scales, updates and lessons for prospecting campaigns. So Kevin, we see your slides up. How about a voice check?
Yeah, can you hear me?
Yes, thank you.
Great. Okay, so earlier this year we had a paper come out in Icarus, a geologic model for lunar ice deposits at mining scales. And this has been fairly well circulated, so I'm not going to spend a lot of time on it. And what I want to do instead is talk about some updates to this work and some new projects that are building off of it. So one of the highlights of this work was this ice favorability index, where we took all of these different aspects of a geologic system model we developed that looked at the sources of ice over time, the capture and retention at the surface and subsurface, and the evolution of these deposits, and wrapped all of those into a predictive model for which locations at the poles should host deep economic deposits of water ice. And in the meantime, we've gone back and we've been able to update this. And so we've doubled the spatial resolution, and we've also adjusted a few things. And it's important to keep in mind that none of the data sets like the neutron spectroscopy or the M-cubed are actually fed into this as inputs. It is a purely forward predictive model from basic principles. But those data sets can be used to calibrate and kind of improve this model over time. And so when we have new data sets coming in from some of these small sats and CubeSats, the hope is that we'll be able to improve those calibrations and improve the predictive power of this product. Now, I've also gone ahead and made a carbon favorability index, and this is not based on any one particular volatile species, but it's based on kind of a complement of carbon-bearing phases. And this might be of interest if, for example, you wanted to refuel a starship that runs on Methalox engines on the surface of the moon. Now, switching gears here a little bit, one of the things that we kind of realized in the early work is that it doesn't really make sense to think about a single episode of ice deposition on kind of a static landscape at the poles. Instead, we have this very dynamic landscape and probably up to a 4 billion year history of ice deposition that's punctuated by the large craters at the poles that each formed at a distinct point in time. Now, those craters, when they formed, would have emplaced an enormous amount of ejecta over the polar regions. And so in this new work, we've teamed up with Ariel Deutsch and Jim Head at Brown, and we've extended Ariel's work to age date craters at the South Pole to estimate ages for the floors of 43 new craters at the North Pole. And then what we've done is created a model that looks at the interplay between ice deposition and the ejecta from these craters in building up these layered stratigraphies over time. Now, similar to Paul Lucy, we've also found that it's really the hydrated asteroids that are the dominant source by far. But because of that, you end up getting into these small number statistics. And of course, you can't have a quarter of an impact. You either have an impact or you don't. And so we think the best way to approach this is using a probabilistic technique. And what we've done is to run a set of Monte Carlo simulations to make 10,000 ensembles of these stratigraphies for all the locations at the North and South Pole. And we're finding some really interesting aspects of these different stratigraphies as a function of the age of the cold trap when it could have started accumulating ice. We've also found in a small subset of model runs, we've produced something that looks more like mercury with a very thick deposit of ice quite close to the surface. And these results are in a paper that's currently under revision in GRL, and so I hope those will be out in the near future. Now, in the meantime, what I've been working on is to take some of those new lessons from that work and bring them back into this regolith gardening model that we described in the original Icarus paper. So this is a fully three-dimensional stochastic regolith gardening model. It includes all of these features and processes here. And the ones in blue are new things that I'm working to integrate into this. And I think the most important one is that in the original paper, we just started with a pure layer of ice on top of dry regolith and then let the model evolve. But I think to better understand these deposits, it's important to take into account these kind of episodic pulses of new ice deposited at the surface and worked down into the regolith. So that's what you're seeing right here. Then the other thing that I've been working on is to take this regolith gardening model and actually start to look at some of the economic geology implications, specifically looking at prospecting. So there's a technique in terrestrial resource estimation called variography. And if you imagine you're looking at a map of an ore body, and the grade here is shown in colors. So reds are high grade ores, blues are low grade ores. And in most terrestrial hard rock deposits, you end up with something like this, where the ore grades are clumped together. And what you can do is create something called a semi-variogram that's shown down here. And this plots a measure of the variance as a function of distance. And so what this shape is kind of telling you is that if you imagine plopping yourself down right here and you measure a high ore grade, you can be quite confident that in the immediate vicinity, you'll also get high ore grades as well. But that confidence decreases as you move away as a function of distance. Now, you could also imagine a scenario like here on the right where the ore grades are randomly distributed. This just looks like a noise function. And in this case, the semi-variogram is just a straight line. And this is something called a pure nugget effect. Now, what I can do then is actually take the regolith gardening model and calculate a semi-variogram as a function of time. And so what I'm finding is that very early after a fresh pulse of ice at the surface, you do end up with something that looks like a terrestrial deposit, where you have this kind of shape, the same shape here that rises up to what's called the sill. But what I'm finding is that quite quickly this evolves to something on the right, where you have this straight line on the semi-variogram, and this is again this pure nugget effect. Now, what does this mean in practical terms if we're thinking about something like prospecting? Well, I think it means that you might not necessarily use the same kind of prospecting approach that you would on Earth, where you go out and lay out a grid of points and drill holes and try and correlate or cridge between them. But I don't think that's necessarily a bad thing. I think it might turn out that prospecting is actually easier and less time intensive on the moon. Now, of course, this is a model prediction. And so the question is do we have any kind of ground truth or reason to think that this might actually be the case on the lunar surface? And I think that we do. And I would point to this quotation from the Lunar source book. It has not proved possible to correlate different stratigraphic layers sampled by coring over any distance on the moon, right? And that's because of this regolith gardening. So I think, we need to ask ourselves, does it make sense to take some of these terrestrial concepts and apply them directly to the moon, where we have a different environment and fundamentally different processes? So for example, what does it mean when we say we're going to go and map out the ice distribution in a given location? And does it make sense to say that we're going to go search for buried ore deposits of ice under the ground, right? I think we have to be careful about what actually translates from the terrestrial world and what might not. Now, okay, so if we want to actually go to and carry out prospecting and eventually mine these deposits, we need to get access down into these cold trap environments. And I think it's important to distinguish between permanently shadowed regions and cold traps. The PSRs are defined purely based on illumination, but not temperature. And it turns out that at the North Pole, for example, only about 40% of the PSRs actually have a maximum temperature below 110 degrees Kelvin. So it's really the cold traps that we want to go down and get access to. Now, this figure here was from a paper that just went online last week. This is coming out of the Robotic Lunar Surface Operations 2 study that's being done out of JPL. And what they had been looking at was some architectures for setting up a mining outpost on the rim of Shackleton Crater. And I think what they realized maybe a bit late is that Shackleton is just a horrendous location to try and set up a mining outpost. The terrain is quite unfavorable. But in the meantime, what we had been doing is working to look at the accessibility of all of the large cold traps at both the North and South Pole. And we're doing this using an automated approach with something called Dijkstra's algorithm, where we can calculate the lowest energy path to drive a vehicle between two points. And so you can see this here on the right. This algorithm is working to find paths between these well-lit staging areas outside the cold trap, going down into the cold trap itself right here. And what you end up with is this branching pattern where all of these branches then converge on what are kind of these superhighways that go down into the crater floor where the cold trap is located. And so what we've done is to calculate all these different accessibility metrics for 59 cold traps at both the North and South Pole. What I'm showing here is kind of a generic measure of the accessibility, where red is bad and blue is good. And for example, we see Shackleton Crater here in the deep red, but there are a number of very accessible cold traps in the vicinity of Shackleton at the South Pole. And there are some attractive options as well at the North Pole. We kind of tend to forget that the moon has 2 poles. So this work is currently under review in Earth and Space Science, but I've put a lot of this data online on my website, and I'll post this link in the chat as soon as I'm done. But you can grab ArcGIS shapefiles for all of these data that have these accessibility metrics encoded in as attributes.
10 minutes.
Okay. And then finally, last slide. So I've talked about a lot of new projects that are building off this original Icarus paper that we published. And the hope is that eventually we can bring all of these analyses together into a single consolidated product, something I'm calling a polar exploration map. And so this would have, base layers, things like these ice favorability indices, geomorphologic units that I'm working to map out over both poles. You can see a sample of that here on the left. And then layered on top of that would be different exploration assets. So things like the cold trap accessibility, these paths, and some things I didn't get to talk about, for example, illumination based on different tower heights. So with that, I will be happy to take any questions or answer them in the chat. Thank you.
Thank you very much. We got time for one quick question, if there are any, and I see there is one. Was it, I don't know, can't say the name, just Dijkstra's, whatever, algorithm that you have used there? Sorry if I missed out. Dijkstra?
Yeah, I think it's pronounced Dijkstra's algorithm.
Yeah,
that's what we use for the cold trap accessibility.
Okay, thank you.